Good morning, Professor.
Good. Good morning.
How are you?
Oh, fine, thank you.
Okay. Good. How's the weather now
Oh, getting much better. Yes, it's we're enjoying it quite a lot. It's sunny and warmer, maybe 8 degrees, so it seems good.
okay. But do you don't have many rain?
Rain, not yet. No,
No.
no. So far, it's been lucky because we have still snow, which is melting. And the worst case scenario is when we have rain on top of the snow. And of course, this causes snow to melt as well as the rain to accumulate. And so it can produce a lot of excess water in a short time. But this year it's been the timing has been good, so that the snow is disappearing slowly, and we're always glad to see that it's when it disappears too quickly, then it causes trouble, flooding,
Here in Mexico, there are some rains now.
Is it
too much hot because we get temperatures around 27 degrees.
yeah. So that's a lot.
That a lot. Yes. But not too bad.
Is it warmer now?
Yes.
Not so cold as it used to be.
Now we have not more cold. Sometimes to time temperature is lower, but not too much.
Okay. All right. Just one question about the book publication. I think I responded in the way that we needed, or your email indicated. So I think is it now complete, do you think?
Yes, this solicitude was from the publisher. They mark the each chapter, and then because they modify some style in the text and ask for some lost information. But now is the publisher who is working in this. I saw that the book is now announced in the in the web page of World Scientist. And there it says that it is for it could be disposal in August.
August. Oh yeah.
August. Yes.
Okay.
Then I think that this will go in good way.
Yes, could be worse, but it seems to take a long time to produce publication now.
Yes, but I think that most of the time was taken by us, because
Mhm.
I don't know if you remember that first we intend to put one deadline before the Congress,
Yes.
but some people don't like that, and then asked to us more time. We first moved to end of the year 2020. I don't remember 21. No,
Mhm.
to the year 20. Then, and after some people asked to us more time, in the way that we only could get all the works. I don't remember, maybe in April or maybe end of March. And
Mhm.
then with this information, we needed to um, I don't remember. Okay, yes, evaluate, and then we start the evaluation during April and until the end of June.
Wow.
And then finally, we couldn't form the proposal. This take some time because it was necessary to organize all the information, to correct problems with the macros that
Mhm.
people use,
Yes.
and something like
Yeah.
this. In
It's
fact,
not so easy for a publication from how many, maybe how many authors in total?
how
Uh,
many, what, excuse me?
authors? How many publications? Oh,
34, 34
54. Yeah. So
publications.
it means you have to have 54 people must all be ready. Yeah?
Yes. Yes. And this was not the principal problem, but it is published preferently in latex,
Mhm.
and there are problems with some package in latex. Then some people use one kind of package that are not compatible with
Yes.
another. And then we needed, we must get the agreement between the authors in the way that we can edit the volume.
Yeah.
But
Oh, well, it's good. So August is good. August should
yes,
be good.
because I think that the editors, that the publisher take around 1 year for
Mhm.
all the publication, the final publication. But they is assigned to us people that work in an efficient way.
Mhm.
They are organized in very good form, and I think the work is um, going in good speeds. In good speed.
Yeah. Okay, that's good. I don't see Dr. Sobchak yet. I didn't have any communication from him, so I hope that we don't have some confusion over the day again. But
I remember that you put the date of the conference in one May. Then, but
well, we could.
I was working with this subject. I do not get too much progress because I haven't not enough time in this the past 2 weeks. Then, but I think that the exercise with graphs is too much instructive for me. That is, I get a better understanding of the problem now. And I think that I was working in putting some of the information that we discussed in the past meeting, but now in my slides latest. And it looks like only some technical work, but I think that it is interesting because I go from the complete graph to a decomposition of this complete graph in two graphs of different weight in the edges, plus and minus. And I think that it is too much illustrative because it's the way that we can arrive to a structure of tree and finally multigraph, and then understand the relation between the different algebras or algebras with different degree. Then I think that it is interesting, this.
Yeah, so far, when I looked at Dr. Sobchak's paper, I think that the application of graphs is quite limited, right? Not so fundamental. That the application of graph theory is mostly, to me, it seems, to be related to sort of combinatorics, like to different ways of writing the formulas that he was talking about in an efficient way. But I'm not sure that well, so far I haven't seen any clear reason for formulating this, the algebra, the representation of Clifford algebra in terms of Grassmann algebras. It doesn't seem to require graph theory as such. I mean, it's only one way of expressing the relationship of the formulas to the signatures of the Clifford algebra. So I'm not so sure of the connection. So I think mostly these subjects are separate, and that the idea of a multigraph is important in itself. The applications of multigraphs and so forth sound, like they could be very useful, but the issues that I see in Dr. Subject's papers are more related to the question of representation of one algebra by another, and so I'm just I feel like I'm a little bit uncertain as to whether or not these should be treated as connected subjects or not. Like even the idea that that duality is somehow represented in a greater generality, if you take this point of view of graph theory, like maybe that connection is stronger. Like it's not so much any relationship to Clifford algebra as such, but the notion of duality, of course, is like basic to category theory, and it's reflected in graph theory as well, of course, in terms of like just simply changing the direction of the
Arrows.
the edges, the arrows, right? So that kind of is very fundamental and deep duality, and when that duality is, that abstract duality is applied to algebra, it gives quite a few different sort of aspects to the algebra. Like in particular, the notion of coalgebra. So we have algebras and coalgebras, and that comes directly from the notions in category theory. But I don't see any requirement or even discussion of coalgebras in the context of Clifford algebra. But I know that the idea of the coalgebraic structure of Clifford algebra was a subject that Zbigniew was quite interested in. Like he definitely had this idea that we should understand coalgebras and apply coalgebras more generally. That for some reason, just historically, whenever algebra is applied to physics, it's always the algebra is always viewed in its not in the co form, right? So in the, I don't know how to I'm not sure what the correct word is for that, right? But so it's the application of algebras as opposed to application of coalgebras. And so he expressed several times to me the opinion that this is unfortunate and that we don't know how to apply coalgebras. It's something like it's a useful notion, but not one that we know. I mean, it should, if we think from the mathematics, I guess, that it should be interesting, but we don't know how or why. And that's sort of I always found that sort of fascinating sort of idea. But just to connect what you're saying is that I didn't yet find or see any discussion of how multigraphs relate to coalgebras, or at least
yes, and this I think that is one subject that we can explore because maybe I'm going to draw some things
Sure.
here
Yeah.
that
Good.
I think that first I'm going to share one one slide only
Okay.
that I was working in, in, okay, I now have here. Okay, it's I only need to go to the okay. Here we have a complete graph of different digger. And those can be interpreted.
I don't see yet your graph.
No.
No, I see only, it says screen broadcast. But,
Now you can see.
No, so far all I see is it says everything on your screen, including notifications, will be recorded. Enable do not disturb to prevent unexpected notifications. Screen broadcast, and it says zoom and stop broadcast. Whoops.
I have some problems. Some problems now with this because when I try to share screen. I don't know if now you can see the slide.
So far, no. I see only that same window. It says you are viewing Jesus Guzman's screen, but the screen I see is only the Zoom notice window. It's a
What's Mm. Um, Um, I, I don't know what the problem here because I
It's not-
tried to share from another pigment, but I don't get. Uh, in fact, some was scratched.
It's strange because I think it is the same method that you used previously.
Yes, it's the same, but some actualization was made during the past week, and sometimes uh, it is not good.
Hmm.
Uh, maybe No, no, I have problems with this because mm, I'm going to one more time.
I see that you are sharing something, but I see only a black screen.
And
Ah,
you don't. Uh,
and now I see again this screen that says screen broadcast, but no other screen.
maybe I don't know if it is here, but maybe we have problems with internet velocity.
Hmm.
You still are seeing the white screen?
It says the screen says it has a red circle,
Oh,
and it has a screen. It says below this circle, red circle, it says screen broadcast, and then it says the word Zoom, and also the word stop broadcast. But I do not see anything else.
because I put how either change to the
Do you do a upgrade of a Zoom or
yes, but I can't. Mm, mm, it looks like a robot. It's not. Maybe it's not working with Zoom now because don't want to.
so you have a slide that you would like to display, right?
Yes, but I couldn't share. No, it's strange. I don't know what's wrong with this. Mm. I don't understand what's the problem.
It seems as if behind this screen that says it says screen broadcast, behind it I see some blurry, some unclear image behind, perhaps.
Yes.
But
Now is the same for me. I have a blurred image.
I can stop my video, maybe.
Yeah, okay.
Change.
Now,
Is it necessary that you approve or that you authorize some action on your is it iPad that you're using? Or Mac?
I don't know if I can share the I'm trying to share quite hard. You can see the
Oh, now is better. I see a white screen window. It
yes,
has a small icon for a pen, I think, or
yes.
green small green icon for
Now
pen.
you can see, but I need to draw here because I couldn't share my screen. I'm not quite, but okay. The
Yeah,
idea.
so I can see.
The idea was this: if I put a complete graph here, oh, for example, I can, in this process of building this graph, maybe I am going to change the color here for the other. Okay, the other
Other direction.
other direction, yes, here, and maybe here. Then we can see, in fact, two kinds of graphics here. One of them is the starting in the vertex 1,
Okay.
and end in the vertex 3. We can say that this is one graph with the weight 1 in the arrows. And in fact, we can we have this way of building 1, 2 in composition with 2 with 2, 3. Equal to 1, 3.
Okay.
But now for the red arrows that we have a weight -1. Then if I need to start from the vertex 3 and there's a mistake here.
Do you intend that? Yeah. Okay. Yes. I meant to ask this question.
Here. Then
Yes.
For the red one, we have now 3, 2 followed or 2, 1. And then we have 3, 1.
Yes.
The blue expression is the composition for the category represented with this graph, and the red one is the opposite category.
Mm-hmm.
Then we have in a complete graph together the one category and the opposite category. And then we have here in this graph the duality principle inside. Then this take or give to us the opportunity of modify the representation of this, and then for the if we follow in this way of construction. Then we have here okay, starting with 1, we have here level 2 and then level 3. here. But this is not possible to build this only with the category, because we need here, in fact, the opposite the category. We can raise this, and we need 1, 2, and 2, 3. Okay, here is the 2, 3. This is possible, but the other is 3, 1. Then we need another color here. Then it is possible only to build in this way, and then we can find the opposite here. For example, in this way, and no, excuse me, because I need a red color here. And now this is the representation in terms of trees of the complete graph. And then we can see that the duality principle is here present is if we build in this way.
Okay.
Because we need the two kinds of operations, the two parts of the category, and this is similar to the Cartan's theorem about the representation of one multivectors and vectors, because here in the first level we have two we can say vectors, E1, E2, and necessary the other vectors is a dual. Is dual to E1 and E2. Or we can get another representation in where we have okay, maybe we can use another symbol, for example, alpha 1, alpha 2, and here Okay, it is better than here we can maybe use alpha. And then
Oh, I see.
with this, in this way, we can get evaluation in two different ways.
How to? How do you express this evaluation?
Okay, we have here, I'm going to change color, a neutral color. Here, it's a problem is one. No, sorry, it's three. Okay. Then evaluation is expressed in this way. F equal to E1, E2, F3. Or we can get this evaluation like E3 alpha 1, alpha 2. Yeah. And this is part of the theorem of Cartan theorem for evaluation. Then I think that it is interesting that this graph can show to us this kind of relations between the different elements that are in the graph. That we have together a category and the opposite category.
But I like to understand here, you have this wedge operation. It's like Grassmann product?
Grassmann product. Yes.
So how do you make a Grassmann product with covector and vector? Well, bivector and covector.
That's not a problem because we can this have degree and these two, in this case is degree 1 and alpha 3 have the degree 1, 2. Then when this have the same properties that the Grassmann product in general, then is anti-commutative, associative, and so on. For example, I think that if we take, for example, Gauss' law in electromagnetic, we have okay, first in vector notation, this is for example here in this form. Then we have the one, the x, oh, sorry. Sorry. That's it. Okay, here we have a product of a differential form of degree 2 and one vector form of degree 1. And here we have a differential form of degree 3. Then we can operate like is shown in Frolinger-Nihenhuis work, the operations between differential form and vector forms. Then this is the idea here.
But here you write this Grassmann product E1 E2. It is okay bivector, but then you make a wedge product with the covector alpha 3, and I'm not sure how. I'm not understanding the notation. If the covector can evaluate the bivector, or vice versa, but I don't see this Grassmann product between bivector and covector. It seems
Bivector and the covector alpha 3.
yeah. So if alpha is covector,
yes.
I don't.
For example, if I have a E1 oh, okay. It's contraction. Yes, I understand your point. It's a contraction.
It could be, yes, it should be perhaps the insertion, or it should be the inner product. Right?
Inner product, yes.
Not Grassmann.
No Grassmann product here. Yes. Right.
So you might write yes, or you could write I think like you might write I
Yes, you can write
alpha 3.
okay.
E1.
E-
E2. Like this.
Okay.
Can you,
Mhm.
can you see what I'm writing?
Yes, yeah, I understand that you
Ah.
say. Yes, I think that is correct.
But iron, okay, if you represent by this dot, this insertion is okay.
Yeah. Okay. Okay. Mhm. Mhm. Yes, because you are putting one evaluation, and only evaluation is better with contraction here. Yes.
But you made a relationship here in the diagram. Um, this is in the graph or the tree structure. You show alpha 3 as it is a arrow from 3 to 1, right?
An arrow from 3 to 1.
Yes.
And
So
then, okay. Mhm.
so you have
Oh, sorry. I need this.
yeah, it's okay.
Yes. Yes. And here. Mhm. Mhm.
And so
And for
so
the
this
loop,
so your point perhaps is that this looks like a composition, right? So we have like
yes.
alpha 2 composed with alpha or well E2 composed with E1 composed with alpha 3. Right? We follow the arrows.
Following the arrows, we can say E1 compose E2. Okay, this is the left branch, and here I need a contraction with
But you like, I think you prefer that that you have just single operation of composition. So you have composition, but now the composition is with alpha 3.
you say this, and now okay.
Yes. So you have just a single operation of composition, but now you have two different kinds of objects. Well, two colors of objects.
Okay. Okay. But I think that it is interesting how this kind of graph and operation of graph show to us the possibility of explore some relation like this.
So this is the reason why you assigned a weight -1. Right?
Yes, yes, yes. It's very minimum. Yes. Because it's a different the connection here is in this way is plus, and in this way is minus.
Mhm. So do you think these weights are related to what Dr. Stopchik was doing in his paper?
Yes, yes, but I think that in the presentation of Dr. Softy, maybe is needed this idea of duality.
Mhm. Well, the kind of duality that Sopchik has in the paper is it seems, or at first it would seem as if the sort of a hyperbolic metric, right? So this duality is expressed in the metric. So we have, say, like we have, say, three basis vectors that are associated with a positive weight and one basis vector with a negative weight. And that we don't, he does not have this notion of evaluation, of course, but this, instead of the notion of evaluation, he's has this duality between the signatures of the metric. Right?
Okay, in terms of signature, maybe
So
it can connect with this idea, signature. Because in the form that Professor Sopsik is expressing, it is like evaluation is equal to E1, E2, dot E3. More or less is this.
but then you would say that so E1 and E2 have a positive weight, so they are like vectors, and E3 is has a negative weight, but he doesn't want to say, of course, covector. He's saying this is a basis vector with whose square is -1. Right?
Yes, because in this way we can think about the E1 and E2 like a space part of the of this system, and alpha 3 like the time part of this. Then we have here this represented in these two parts of the graph. And the change of signature is to go from here to here.
So far I don't see the relationship between this covector and a basis vector with a negative weight, or like, so somehow you're proposing that if we have a basis vector whose square is 1, it's like a vector, but if we have a basis vector whose square is -1, then it is like a covector.
Yes, like are covered this way.
But what product? Like in Clifford algebra, we have only this Clifford product. I don't. The Clifford product of a vector that has a negative weight is no different than the Clifford product with a positive weight. It's
I don't understand your comment related with.
well, if these three objects, like where should I draw? These say the okay, let me just draw something. Come on, you're not going to let me do that. Draw. So if we have this object and this object and this object, instead of composition, if we had Clifford product, then this object would be 3 vector, right? It would be, but in this case, so the weight would be maybe +3. I don't know, but you would like the weight to be 1, right? Because this is weight of 2, and this is weight of -1. So composition weight is 1. So we get evaluation. It makes sense, right? But if we have the Clifford algebra, we can't simply just replace the composition with the Clifford product.
No, I understood the point.
So, but we would like in Dr. Sobczyk's Clifford algebra to express evaluation somehow. So I think that to do this, we need alpha 3 to be a trivector, for example, right? To a 3 vector, and then the product of alpha 1 and alpha 2 is a bivector, right? But the composition of the bivector plus the trivector has 2 parts, right? It has one part that's weight 1, and one part that is let's see, one part that's a scalar, I guess, right? So then we could represent the evaluation, provided that we can distinguish the degree, right? So if we can, so when you write the dot, right, it means something like take the scalar part, or take the vector part.
No, because we can we need to say that these have degree 2 and these are 1 and 1. And now here this have degree 2, and here 1 and 1. Only in this way evaluation have sense because both objects need to be of the same degree.
Yes, or alternatively, we need the Clifford algebra structure in the Clifford product, right? So that we have this splitting of the different degrees, right? So we need like a scalar product, and we also need a Clifford product. But we express the scalar product in terms of the Clifford product plus this thing called the Frobenius structure, or the trace, right? That takes the allows us to express the how should I say that?
Because I didn't understand here E1 and E2 and E3 like E1 is vector and so
Yes.
and alpha 1 is related with dx1, for example. But alpha 3 is in fact the product of dx1, dx2. And then the same is for E3, is the product of E1 and E2. In this way is the how the degree of these are related.
Okay, I think it's interesting, but still not, I don't know if I understand the full implication. How?
Yeah, I think that the implications are related, but we with trees of higher order that are only clonations of this tree. For example, we have here this and this. And then we can get one clonation with this, but it's going to here. and this here. And so this is related with a complete graph of degree 4. And for 5, I need to clone this to put inside of the next degree. I forget again the word the past session you said to me how we get this operation here, the grafting.
Mm-hmm.
And we have here a process of grafting with the same, but then I get a higher order of graphic. And if those are related with Clifford algebra, then we get relations between Clifford's algebras that are expressed in this way. Then I think that okay, it is necessary to work this more, but I think that it is interesting to explore this idea.
So you introduced this grafting. Can you return to the previous page?
Yes. Okay.
Yes, this. So. So now if we were to draw the directed graph for this structure, we would have 4 nodes.
Yes.
Like 1 node for each level. And when we have an edge in the tree, we have an arrow in the graph. Okay, let me try to understand.
Because here is the...
You should have a different direction, right? We must have a different color of the edge.
Okay. Then we used different color here. We have here. And yes. Here we need to erase that. And that.
Yeah. Okay, now with this color, we know what direction to draw the arrow in the corresponding graph. And this is a picture of a tree, but it has a tree with 2 different colors of edges. Right?
Yes.
And you would like to make this correspond now to a graph, or to a graph. So we have 4 levels. So we have like, so this is 1, this level is 2, this is 3, and this is 4. Right? And so now we have like 1, 2, 3, and 4. But now we draw edges, right? So we have
Yes.
edge from 2 to 1.
Yes.
We have edge from 3
2
to
1,
2.
and 1 to 2, and 1 to 3.
4.
Okay, we are in,
But we must use now a different color, right? And we will use, we would not write
maybe I can try if you like to draw the arrows, or you are not.
okay.
Because I'm going to erase these arrows and
Sure.
then try again. The black one, starting from 1 to 2. Oh, sorry. 1. This is 1. Now we go from 2 to 3. And from 3 to 4. This is one way.
Okay.
The other is from 1 to 3. And from 3 to 4, but this is yet here. And only that. And now we can change color and go from 3 to 2. And
3? No, I don't. No, I don't see 3 to 2. It's not,
sorry,
not
it's 4. It's 4.
Yeah, 4 to 2.
4 to 2.
And also 4 to 1.
4 to 1. But we need more. No. Because it is needed the complementary part of this that are here. Now, now. Here. Okay, and I think that this is here.
Okay, yeah, so this is the opposite tree.
The opposite tree that is needed with the complete graph. And then We have here mm, to here. Mhm. And to here. And then this 4. 3, 2, 1. Mhm. Okay. Now for the letter 1, I think that this is from here to here. Okay. Here we have this and this. And something is I'm going to explore here before to continue because now we work with the branch left branch, then we start in 4 and go to 2, 4 and 2. But 4 and 2 but it is needed is 2 to 4. Then 42.
Hmm.
Okay, now
What do you do with this opposite? Well, maybe it should be called the co-tree. Right? We have a tree and a co-tree.
yes, but because I need this that is
4.
from 4 to 2 but now from here to here, but the how you say in the core tree. And now I need to go from 2 to 1. From 2 to 1. But then I need a red here. Let's here. From 2 to 1, and I need this. And after I got from 4 to 3, 4 to 3, that is this. From 3 to 2, that is this. And from 2 to 1, that is yet here. And after I need to go from 4 to 1. 4 to 1. But it's black. And now
Oh,
4 to 1 naturally, but it is needed here. Now I am inverting the arrows, the black arrows.
uh-huh.
And after I need to go from 4 to 3. 4 to 3 is jet, and
It's
3
here.
to no, sorry, this is not here. This is not here. Mm, 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 Only that. From 4 to 1. But now jet is jet now. Now we have a complete graph.
Mm.
I think that I
Something
need to
is missing.
something is missing, yes, because here okay, I only invert this
1
here,
to 3.
and now 1. Okay, I need here, and I need here.
Mm.
No,
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 no, I think only you need is this.
this. Oh, okay, yes, yes, because it's the image of
The one above, right?
yes. Okay, then we lost 4 to 3. 4 to 3 is jet, and 3 to 1. 3 to 1. Okay, 3 to 1. That is red.
As you said, of course, we have this now complete graph, right?
Yes, now we have a complete graph. Yes.
But it is the definition of this co-tree, right? The co-tree is necessarily the completion of the tree, right? Is the
Yes. But how you can see, we have in what trees the combination of vectors and covectors.
oh, okay. So I think I need to think about this more.
Yes. Yes. But,
So from this, somehow we would like to have like this tree and co-tree is a kind of categorical kind of duality. But from this, we would like to get the kind of duality of linear algebra. the algebra in its dual.
Yes,
Oh.
yes.
So, because we think of the covectors as living in the dual space, right? I And then in addition, we have the other kind of duality that Dr. Sobchak is talking about, which is, I'm not sure how to describe it, but it's like the signature of the metric, right? It's like the relationship between the vectors whose square is 1 and the vectors whose square is -1. So we have really 3 different kinds of dualities. Do you think that's correct? That we have the categorical duality, and then we have the linear algebra coalgebra duality, and then we have the signature duality of the metric. And somehow we would like to see these three different dualities related to each other.
I think that these two are related by the Cartan's theorem, because in the Cartan's theorem is a vector of degree p and covector of the same degree. And then we get through this an scalar. Then we can see the degree here. For example, this is the red one that is at the right in the upper tree. We have 1, 2, 3, the degree of this. Three. But here we have in the degree 2 and degree 1. Then we have the same, and then get evaluation. And the same can be put here 1, 1, and here we have 2. Then we have a different kind of ways of with these vectors and covectors. And then and this is that is shown here in this tree, the different ways that we can build that.
So you think when we draw this complete graph, some of these arrows should be shown with different weights, like -3. So we have this arrow from 4 to 3, like this arrow.
Yes, okay.
From 4 to 3, we should say
they are going to have different weight.
-3.
Yes.
But we have this arrow 4 to 1. It has a weight of +1. This one. But we have 1 to 3. Oh. Oh, just a minute, 4 to I'm sorry, I should not put this, not this, but we have this arrow from 4 to 3. 4 to 3. I must be more careful.
Yes, but I think that it is like a commutative diagram. Because if I have here this, in the way that this is FG, we can see this like if follow like G, but we can see in this way F G, and we can invert this, and this is F G in the opposite category. And it is when we have evaluation.
Right, just one moment. I have a problem with my audio here. Why I don't have. Something went wrong with my audio.
I'm going to organize this information, and I am go to see what's wrong with my equipments, but because I have too much problems today on sharing.
I'm sorry, I don't know what's wrong with my audio. Just one moment. Maybe this is correct?
Excuse me?
Ah, okay, sorry. I have some problem with my audio. I don't know why I lost connection.
Oh, okay.
Now I have, I can hear you again.
Okay. No, I said that I'm going to try to organize this information and look about what was wrong with my equipo.
Uh-huh. Yeah, I think it would be good to see this in a more complete manner. It's difficult to do all your to express all of your ideas here just on this whiteboard alone. But yeah, it would be good if you could set this out in more detail in a few slides. I think I almost see what you're saying, but it's not entirely clear. But to me, it seems like we replace just how should I say, like this relationship between the opposite categories and the arrows in the opposite direction, of course, is obvious. But when we label these arrows in a single graph with both F and G, and also with composition of F opposite with G opposite, then it's strange, right? This labeling is not expected in category theory as such. Or maybe it's better to say that these arrows are in different categories. So it's difficult to see this as composition in the usual categorical sense.
Yes. And then we must
you know what I mean, like, so yeah, so we would like a different color, right? So
yes,
so it's
because those are different categories.
In different categories. Yes.
Different categories. Yes. Yes.
But okay, well, maybe this is enough for us today. We can agree to meet again. What is best time for you for the next meeting?
Maybe next weekend I can I have time, but I don't know if I have enough time for prepare all of this. But for me, the next week can be, or
It's possible.
2 weeks.
Okay. Well, I will try to contact Dr. Sobczak to see the status of his time, to see if he's available for the next meeting. If he's just to be clear, because I did send him an email while we were speaking, but so far I don't have a reply. So I will confirm with you if he is available, say in 1 week or in 2 weeks, then perhaps we can try again, maybe to combine these ideas, like two presentations, because I think initially he was going to make some presentation today, and you also would make some presentation today. So, but now at least we discussed more the ideas that you have, that you would like to be able to express in more detail. So if you have time to prepare something, and when Dr. Sobczak is available next time, I will let you know. Maybe 1 week or 2 weeks, or I will see from Dr. Sobczak what would be the most suitable time. I
Yes.
assume he had some difficulty or some misunderstanding. So, okay, so I will send you an email to tell you
Okay.
what we decide. But we could expect, I hope, to at least at our next meeting to go in a bit more detail about what seems to me to be these three different kinds of dualities, and how these three different kinds of dualities might be related through your approach. Okay.
Okay.
All right.
Great. Yeah,
I hope also that you can resolve the problem with the screen sharing. You had this problem too.
I'm going to see what's wrong with them.
Okay, if at some point you would like to do a test, you could send to me just to send an email and say, we'd like to try to make sure that this screen sharing is working.
Okay.
We could just take a few minutes to check.
Okay. Okay.
Okay, great.
Great. Thanks.
So see you soon. Bye-bye.
Bye.